Okay, we're actually recording, unlike last week. Do apologise about that. So this week, we'll try and keep the lecture fairly brief, because we'll have a break, and then we'll have a break, then we'll then go to the tutorial session, and the tutorial won't be that long. I have uploaded the full tutorial, written instructions word for word, online as well. So if you're not able to make it, or you want to go over it again, it's all there for you. We are assuming that you've all got some level of Microsoft Excel experience. We're going to add, I think there's 3 tutorials on Excel and the rest are then workshops. And there's 3 tutorials, try and not miss them, because we'll be showing you quite complex stuff in there in the latter part. Look, today's quite fun, today's quite good, but I think the other 2 are really important. Okay, on the middle page, I was just conscious that I have uploaded a few things that you may or may not be aware actually are there. So in the general teaching materials, I did upload my notes, which I did show you before, I believe, but just in case you missed it, these are the notes that you'll be getting. I've got a copy that I'm going to show to the class just now. You'll be getting a copy of, these in the exam. And if we do a mock test, I don't know if we will. We'll have a look at the calendar, see if we've got a mock test planned. If we've got a mock test planned, I'll print out a copy of that for you as well. When it comes to the actual class test, what we'll do is you won't be allowed to bring anything in other than pens, no pencils, pens and calculators. Maybe a ruler, but that's it. I'll hand you out a clean set of these. Okay, all sounds good. What else have I done on middle page? I don't know. I think I've done much else. Yeah. For the people that I need to make that a bit bigger so I can see a bit better. For the people that done the tutorial last week, there wasn't as many as I thought there would be. What I'll do is I'll give you individuals written feedback. I'll give everybody, I'll upload just the answer for those that want to just double check. You got a problem, then talk to me. If you can't work it out, then I'll perhaps release the solutions later on. But I think just to encourage people to do the tutorials, I will give individual feedback, like written feedback. Right, okay, so that's for this week's one. We do have, I will give the full answers at some point, but just at the moment, no, just try and do the weekly stuff. It does help. For this week's one, we've got the lecture slides here. I'll put today's recording up here if it all pans out well, and we've got an additional tutorial for you to submit. It will close Monday morning, so try and upload it before Monday morning. Okay, let's go straight to the thing. Slideshow from the beginning. Can I make this any smaller? Right. Cool. Right, okay, here we are. Right, today we'll be looking at the shear load displacement and the stress-strain relationship. I know you've covered the stress-strain relationships before with Juan in first year, but we'll be looking at it in a bit more detail. We'll be using mass, density, and weight within some exercises as well. So these are the notes that you had from before. Again, you just seen these 2 seconds ago. That's the first week, that's the second week, and today, let's have a look at this. It won't take too long. Right, Again, you've seen this scenario before. We're going to look at a very small part within a larger structure. We're going to call it dV, dV meaning the volume, small volume, a subsection of. And there's our orientation there. You've seen this before, axial withdrawal, pulling it, axial withdrawal, tensile pulling, sorry. Hi guys. Oh, that's a valid point. If I just temporarily pause what I'm doing, because I am a bit of a silly person, we do have a check-in code for today. There's your check-in code there. Oh, sorry, you're not seeing that, are you? Mousey, where's the mouse? There's your check-in code there. Can you please just do that just now? Hopefully this doesn't go everywhere. Everyone got it? Cheers. We've only just started, guys, so maybe get your notepads out. We're kind of getting to the point now where this is like, what, 3 weeks worth of notes you'll need just to answer some of the questions and tutorials. So your notepads out will be a very helpful thing. We're looking at, just for a bit of recap, I'll go back a couple of slides. We're looking at today the shear load displacement, like shear, where before we've done pulling and pushing. Now we're doing shear. Right. So object, pulling it, that's what we've done before, but this time we're going to be looking at the shear. So oh, that helped. It's probably going to make a bit of a mess. Let me just double check. Right, we're still recording. Right, and sorry guys. Okay, let's go back one slide. So what we've got here is we've got the load being applied. Can you see? You can't see my mouse. That's such a shame. Oh well. The load being applied here and shear. The load being applied this way, okay? Horizontal load. As you see, it's going to deflect, and you'll have a displacement here. But that's not a displacement in millimeters, is it? It's a displacement and an angle, isn't it? An angular displacement, or it would appear to be so far. Right, so if we've got tau yx going this way, then you'll find the equal and opposite will also appear here, right? So we're not losing any energy, and energy is still there, it's being resisted. So just make sure you understand that will be resisted there, and then that will be resisted there. I.e., if you've got an object like there's my mouse, and I push it, if I push it at the top, it's probably a bad object, but mobile phone. If I push that object there, I need to be able to resist it at the base as well. Right, so I can resist it by putting my finger here, it's resisting it, but also wants to lift if I push too much, and eventually at some point the hold down there will be required, and that's the very basis of, well, you hear more about that in the other modules, but for this, just see that those loads are equal and opposite. And so there's our first equation. Please write this down. G, shear modulus, we write it down as G. Now shear modulus of elasticity, we saw last time we referred to it as E, but this is shear modulus. To distinguish between the two, go and write it down as G. And I'm also painfully aware that last week that I may have misled a few people, because I said in my text, I said, look on Google, but I then gave you the answer underneath it. So I apologise for that. I know one person got a wee bit, but they got it. I'm sure they understood it well afterwards. So here, let's just try and keep our notations correct. If we're talking about shear, let's use the letter G rather than E. Okay? I remember one year I explained these equations as being all the same equations, just use different letters. That never worked. So this way, that didn't click with people. So this way, yes, the structure of the equations are quite consistent, but just use G for that shear, just because otherwise you may get confused. Right, let's crack on. Now, obviously, we're looking at a small part within a larger part, obviously. Where's my mouse? I'll just use this again. So we've got that as our first equation. There's our second one. T. Now, in one of my examples, I've still called that F. T, F, that's fine, I do apologise. When you come to see one of my tutorials, I've still referred to that as F. It's still a force. Okay? So force equals K divided by L, all multiplied by delta. You've all seen this equation before. The only thing that's different is the shear load displacement relationship. We've replaced F with T, and I get it. It's still just a force though. So that means there's a distance in millimeters or meters or whatever unit of measurement we have here as a displacement, but we've also got this gamma, you'll see that in a second. Right, so we've got a relationship here. Yeah, you can see I've just rewritten that as F there, just to say, look, that's the same equation, just that we're using T to refer to this force that has been applied in a shear action, but still the same thing. We've seen this before. That's area, breadth and height. Now, let's make sure we understand what it is we're talking about. The breadth and the height. How did I explain that before? I think what I'd done was I used a lever arm approach. Imagine I've got a ruler. I should have just brought one. There's my pencil, right? A moment. You all know what a moment is? Force multiplied by lever arm. And you've got a moment where my hand is. That's a moment happening there. That distance times the force. So that would be your length, okay? Lever arm. Well, here, you've got a force happening, the exact same thing, isn't it? Well, if that's going to be the length, then that way you know that that's the length and that must be the height. Or try and think of it in such a way that the penny drops for you. Because for some people, knowing what the height and what the length is might be a bit confusing. Make sure you can work out a way that you understand. The way how I do it is work out the lever arm. The force has been applied like that. So that's definitely my lever arm. That's my lever arm there. And then that's going to be my height and my breadth. So my area is going to be this area here. Good? Excellent. Right. Mousey. Okay, let's use this. So that's area, T being the force, and tau. Perfect. Again, my little triangles, where would I be without them? I just done this one in red just to say, look, this is exactly the same as we've seen before. Force, area, stress. Tau is stress, but it's in the shear format. Just the stress, force over area. Force over that shear over that area here. That's the force. It's not acting down the way, it's acting horizontally on this scenario. So you can see why I did say to some people, you only need to remember a small number of equations. It's just that you need to manipulate the equations depending upon if it's a stress this way or a stress shear stress. But I think for you guys, because you'll be getting the sheets in the exam, just try and do it, just do it the right way. Just look at the equations and then use them appropriately. Okay, so what have we got next? Yeah, we've done this once before. What have I done here? And this is this here, or for people in the video, I'm referring to this angle here. Tan y divided by 1. Yeah. We are looking at a very, very, very small part of a very, very larger structure, hypothetically. And when I say to you, it's approximate, that approximate is good enough for all of science. Okay, I did look at this in more detail a number of years back, and I found that it does hold nicely. So, if we just simplify delta, meaning that a millimeter displacement divided by L equals that, then what we're then getting is delta is approximately gamma L. Okay? So just go with me on that, and it does work. And then it all done? Cool. Again, there's my triangles. And as you've seen before, this is the strain. It's the same thing, it's just that again, it's shear strain rather than strain because of pulling. Okay, it's that movement of caused by the shear, the horizontal shear. Okay, why did we jump to that? That's correct. That's right. So if we take T, so we started off with this up here. Sorry, you can't see what I'm doing. We started off with this here, and we know what T is, we know what delta is now, so we can convert that. And we've now got T, so T is the force, remember, equals G, which is the modulus of elasticity, but in the shear action, multiplied by the area, divided by L, all multiplied by delta, delta being this. Okay. What we're seeing for the shear stiffness, the panel has a function of material properties, G there, and the panel geometry, area and length. Funny that, it's exactly the same as what we said before with axial withdrawal, or sorry, tensile withdrawal or compression. So it all holds true. So, plane stress, so we saw this before. from equation 3.9. Now 3.9 is actually from last week. Just a bit to recap for you. This is from last week here. This is what we saw last week. 3.9 is this part. So from that, sorry, how did I jump from that to that? Yeah. So from that, we're going to take isotropic material. It just means a material. So this wouldn't be timber. This would be things like metal, or I hate saying things like concrete because it's not true. Concrete on the bigger picture, right? Like large scale but not small scale. But like steel, this would be true. This means a material that has the same property in any direction, irregardless of how you test it. Okay? But on a small scale, we would say concrete is that, we would say, on the large picture, but on the small scale it definitely is not. But we'll assume that it is just that, right? Just for simplicity. But steel, definitely, aluminium, copper, materials like that will have the same material properties in any direction, irregardless of how you apply the load. Right. Only two independent parameters. Hence, if we've got two, the other can be determined. What I'm referring to is the E, the G, and the Parsons ratio. So, mechanical properties we've seen so far: elastic modulus, shear modulus, and the Parsons ratio. There are other important material properties, i.e. the density. We'll call that rho, right? And rho is kilograms per meter cube. In many structures, yep. This is actually very, very true. Remember me in first year, and I brought out a small section of I-joist timber, and I said this is very, very light, but this is stronger than the larger piece of wood that I had, and it was a glowing beam. I said this I-joist is stronger than this. They were roughly the same size, section-wise, and what that was because is because the your beam, if it was a full-length beam, the I-joist is much lighter, and therefore it's not having to carry its own self-weight over that long span. And we then talked about the second moment of area we talked about, and you learnt more about that from Juan later on. Why am I telling you this? So in a structure, the self-weight of a structure can be really important, especially in large structures that I tend to get involved with. And so you do want to be very mindful of what it is you're building it from. Okay? Going off topic now. Let's try and go back on topic. Right. How do we calculate the dead load? Right, dead load is an old-fashioned term. I probably shouldn't have done that. I'm just showing my age. We now call that permanent load. Okay, if we want to start getting our head into the correct mentality of structural engineers, we would have permanent load and variable load. So I really should change that slide, called the permanent load. Dead load, just it's the exact same thing, just older terminology. And the reason why we have that terminology, so when we're writing our calculations down, we're being consistent. So we should get our heads around permanent load. Permanent load, permanent load, what would that be written down as? Does anyone remember? No, I'm totally off topic now, but we're here, so we'll talk about it. GK, capital G or small g, meaning G means permanent, Q means variable. You heard this before? Right, and K means characteristic. So it'll be a small letter K but subscript. That just means it's characteristic value, right? 1/5 percentile. And then you've also got the designed value, right? But that's not for this class. That's for your structures class. Right, so for the dead weight or the permanent weight of a building in newtons equals the mass times the gravitational acceleration. How can we make something so easy so complicated? We can do it quite well. Um, I know when you do work with Mark Taylor, I will guarantee he'll give you gravity to probably more decimal points than what I've given it to you. Yeah, well, see, it all depends upon what it is you're calculating. When I'm doing my large projects, that is good enough for me, right? Well, actually, I don't use that, to be honest. I actually use soft. I use Techo TEDs, which you've all used before in first year with me. I use Techo TEDs, and it's got gravity built in as a stated standard. Even although it's nothing standard about it, gravity changes from location to location. Not unless you're a flat earther. Then gravity doesn't exist. It's just buoyancy. Sorry, I'm recording this. I shouldn't say this nonsense. Right. Just to make sure you understand, I'm not a flat earther. I'm digging my own grave here. Right, sorry, get back on the track. And if you are, I apologise. Right. And if you were, we'll take out a total station and prove you wrong. Right. We should do that for fun one time, actually, just purely for fun. Because you can actually prove it with two posts, a total station, and a long bit of concrete. But anyway, very long bit of concrete. But anyway, nonetheless. Um, and mass density times volume. Okay. So the force, or T for today, well, we would just refer to that as T, not F. It would just be rho times V times G. Um, what might be helpful for you? I know it sounds silly, but go and just do it anyway. Go and write down this part of the equation, please, and get your head around this. See, when you start to use software, I would just please write it down though, yeah? It'll sink in better. When you start, I would write it down, guys. I would just do it, try it. When you start to use software and you mess up your variables, things in software won't work and it'll say they'll just throw up an error. Um, let me rephrase what I said there. If you use Microsoft Excel, it won't throw up any errors. It will just give you the wrong answer, right? And you won't know it's wrong, and you'll just mess things up, right? Hence why structural engineers would tend not to use Microsoft Excel if we've got a better solution. So things like MassCAD, we don't tend to use MassCAD because it's very, very expensive, and it's tend to be more for scientists. Um, We use other things like TechOTEDs or other calc packages because it's a lot cheaper and it's good enough for what we need, right? But if you're a researcher, you're going to probably use MassCAD, to be truthful. Right. And in those softwares, you put the variables in and it would know what the units are. And if you multiply something together and ask it to show it in kilonewtons, and what you've got is not a kilonewton, it will tell you that. Excel won't. So these softwares keep you honest and check that you're doing something right. Anyway, and we want to be doing the same thing by hand, which should be checking when we're multiplying things together that we have got our units correct. And that's only possible if you understand what units are in the first place. So, right, that's the end. Well, not quite. This is my notes, what you should have written down today. This is what you should have written down at least. The only thing, what is the volume of a sphere? I don't expect you to know that, right? What I used to do in this module is I used to then do a silly exercise. Oh, I thought I had the slides in. Did I not? Oh, that's a shame. I used to do a silly exercise showing people. Oh yeah, there's the exercise there. Um, the proof of where this comes from. Very quickly, tell you a silly story just as a side tangent. I was at a pub quiz and a whole bunch of scientists and one engineer, and none of us could remember what the volume of the sphere was. So out of what 5 is, 3 of us calculated it by hand. We all got the correct answer, but we all done it different ways. So there's multiple ways to prove that. I was just using, when I was doing this, I was using calculus to do it. But you can do it in different ways. Right. So just know that you need to know what the equation is, or at least find how to get it. So this is your exercise for today. Now we are running quite good with time. Oh my word, we're doing very well for time. This is actually quite bad for me. Right, we're only 40 minutes in to a 2-hour lecture and we're almost finished. Hopefully the computer lab's free and we'll just go straight there and we'll get the computer lab stuff out of the way and that'll be us. Right. Okay. This is quite a nice exercise actually. I quite like this exercise. It's quite good. What are we going to do here? We're going to look at a 10mm thick steel plate has been fixed to the left side. Now at the moment I'm doing an awful lot of metal brackets. Sorry. I'm a consultant engineer for an external company and I do that and I actually employ people. So last year I employed 2 people from this room or from this module and they still work for me. And we do structural calculations for what we call SCR, or for building control, for a real company. This company does mass timber buildings. I can show you photos, maybe when they're in computer suite. I'll show you photos. Where at the moment we're doing an awful lot of metal brackets, where normally we wouldn't do metal brackets. And we're doing them because of this one particular job just is they want to use loads of metal brackets. And some we can buy off the shelf, but some we can't. So I'm having to do stuff like what we're doing here for real life projects, right? So let's say I am. Lawrence and Danielle are. Right. So we assume that this is fixed to something solid, it's not going to move. So that's stationary, right? What's also, before we get into the rest of the text, that's what else, we can see if that's fixed stationary there. That's the cantilever. There's our T or F, whatever you fancy. So that must be our length. Our length is the cantilever, right? Well, I've already given you that in this slide, but just remember, if I didn't give you that, if I didn't give you that's L and that's H, you should be able to know instinctively what L and H are. Okay. The sphere has a radius of 0.816 meters. It has been hanged to the right side of the plate by considering the following data. L is 1.5 meters. Where's H? Am I being blind?
The same thing. It says up at the top.
So it's, thank you. L and H are the same. So it's 1.5 meters, 1.5 meters. R, well, we have that from over there, 0.816 meters. B is just 10 millimeters. The G is the modulus of elasticity for that plate, right? It says it's a steel plate, but we've used a different material, so we'll call it metal of some sort, right? Because that's not what we would normally expect. So we should see a bit of movement in this one. Because steel is normally 2010,000 millimeters squared. Yeah, units per millimeter squared. And this is only 8,000. That's more like timber, to be honest. That's fine. We're okay with that. Right, and the sphere, well, we've got rho. Rho means density, is 7,800 kilograms per cube. Compute the vertical displacement at the top right corner up here of the plate. We're going to ignore the elongation of that rod We've not been given any information about that rod. Right? We're only looking at the shear movement of that. That's all we're going to do. We'll give that a wee shot just now. And what I'll do is I'll pause the recording. So that's the recording back on now. And what we'll do, I'll get my iPad out. So one person's got the correct answer, 2.16 millimeters. And we just talked about, totally aware, and we've just talked about the how many decimal points. There's no right or wrong answer. 2.16 is absolutely fine. I've got 2.158. You know, 2,000ths of a millimeter. You know. But again, it all depends on the scenario that you were talking about. On a large building, you know, keep it to the nearest mill. If it's something like this scenario here for this sort of example in this class, more decimal points the better. But all depending upon a number of things. Right, I'm going to try and change over to my iPad. Cool. And we'll come out of that just now. I'm going to assume you all have your own notes, because me trying to show my notes at the same time is a bit, because there's too many now, if you know what I mean. Yeah? Hence why it's good to take notes during class. And it's also good to take notes also because just the act of writing things down, you might never go back and read it, but it helps it cement inside your long-term memory. Make sure this works. And I've got my scribbly notes here. And for some reason we're not syncing. Why are we not syncing? See, after all of that. Why are we not syncing? See, it works perfectly. So there we are. It works perfectly sometimes, and at other times it just doesn't want to play. Right. There's definitely a lag on this. There we are. Well, hopefully this lag will disappear as we go. Right, so there's our question. Now, on the actual slides, we have all the answers anyway, so you're not going to miss anything out. And what equations am I going to use? I am going to pull this week's notes over. Right, you've all seen that image anyway, so that's fine. So the first thing I'm going to do, I'm going to write down what it is I want. A pony? No, it's not a pony. I'm after this displacement. Sorry. Make it bigger so I can actually see what I'm doing. I'm going to use my equation 4.4. Okay, so my 4.4 equation is that one there. Okay, so I'm going to just write down that. Obviously I know what L is, but I don't know this yet. So I'm going to write that down. I'm going to find an equation that I get that from. Well, I know I can get it from this silly triangle thing that I always draw. So I can go there, I can go tau g. And that's from equation 4.1. That one there. Okay? So I'm just sitting playing mix and match at the moment. And then, what do I have? Let's have a look. What do I actually have? Do I have G? Yes, I have G. Do I have tau? No, I don't. So I'm still after tau. So I'm going to fire down tau. I'm going to use equation 4.3. 4.3 is obviously this one here. Right. In my slides, I will have that shown as F. I apologise. Don't hurt me. Somebody last week sent me an email. I'd misspelt something in a video that I'd done. Like something heinously horrible, like got two letters round the wrong way. I got an email about it. Fair enough. Sorry, yeah, what am I doing here? Yeah, it is 4.3 force over area, breadth, and height. Okay? Force equals mass times gravity, or we would go rho v. Sorry, that's get a bit more correct. G. And G equals, sorry, my handwriting is amazingly bad. I apologise. What I'll do is I'll make that all a bit smaller so we can actually keep it on the screen. Is everybody with me so far though, yeah? Everyone's following me. And it is just repetition. It's just to sit some blank paper and just sit and go through it. Do it enough times that it becomes normal, you know? Then, right, obviously it's the force that I'm after now. I know what rho is, I know what G is, I don't have V, so it's now going to be the volume. Sorry. That volume is what is it? 4 over 3 pi r cubed. Okay? I don't expect you to remember that equation. even though we probably should. So with that, what you can see on the screen here, can people now calculate that and work their way back up, please? And for the people that had done it, is that how you done it?
I just plugged the value for t into the t equals g over L.
Can I have a look? I'm going to
The
just pause this just now. Hold on.
the float on your notes.
Yep. So the final answer should be 2.158 millimeters, or to however many decimal places you happen to calculate it to. As long as you're able to understand the method of pulling out the data that you've got, working out what data you need, and then using the equations that we've had over the various weeks, pulling it back up. I know we've got the volume of a sphere, but I've given you that in the sheets. You'll have that in the exam as well, so that'll be absolutely fine if you do come across that, which I'm sure you probably will, hint hint. So please get your handle on this problem here. I can't be any more helpful than that. Make sure you understand this problem. It will be different from this. You'll have to do extra steps that you're not doing here. But if you can handle this problem comfortably, right, then you will have a fighting chance. Like a really good fighting chance. Right, we'll take this away just now. And we'll go back to so we can see we've got all the steps written out. The volume, we've calculated it for you, so you can just double check that I've got the same as what you're getting. And there's the answer. Or alternatively, is this how you done it? Did you do that?
Yeah.
You see? How much easier is that? How much easier it is just to do that than it is to do all the nonsense I was doing. Did anybody else figure that out? You did? Cool, so the two of you got the same method, where it was Finlay, who is not here today, done exactly the same thing on week 2. He had done something, he'd done the same equation in fact. He used this equation on week 2 to do something that took us a long-winded way to get the answer. And so this equation's got G rather than E. It's the only difference, right? Always look at, is there more than one way of doing it? Which way is going to get me the results faster? Or better still, can I do it this way, get an answer, do it that way, get an answer, and double check that I've not made a mistake? Because sometimes, I know on one occasion, Adrian messed up big time. He used 0.8 meters as a unit, and it should have been millimeters, and it just knocked the decimal point out a little bit. Imagine you'd done the same thing here, you messed it up here, but you then ran it again, you use it as a double check, which is really handy for an exam situation. Right, this is the tutorial for next week. Please do me a favour. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 people in the classroom today. There's other people who've emailed me saying they couldn't make it, which is very helpful, and I do appreciate. If you're not going to be able to make my classes, do email me, let me know. I don't need to know why, I just need to know that you're not going to be there, so I know that you're still still looking at the material, you're still keeping on track, and I'll try and make sure I record it for you. If everyone's going to turn up and nobody emails me in, my recordings might not happen because it is a pain in the backside. However, so I encourage you all to do this one. It's a very similar exercise. This time though, we've got a 10mm thick plate, L is 2 meters, H is 1.5 meters. I've given you the orientation of L and H. Again, cantilever, length, height. So it's very similar to from before, just that those numbers are different. Thickness is 10mm, not 8mm. And there's the G of the plate again. I think it's the same as the last time. Oh, nice. Blah, 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 blah. Right. Calculate the dimensions of the concrete ballast that will give a vertical displacement of 5mm at the top right. It's a weird question, but please do it. So you want to calculate the size of that ballast. It's going to be like the volume, right? So the size of that ballast, to which will give you a 5mm displacement. Have we said what the ballast is made out of? Excluding any elongation of the rod.
So this is concrete.
Where does it say that?
Big paragraph just above the displacement.
Concrete. Right. So on this occasion, unlike where I got email from Dion, where I had last week given you a unit, I gave you a variable, and I said go on Google and find it, and I then gave it to you anyway. Sorry about that. On this occasion, I don't think I have given you the density of concrete. So you'll have to go and figure out what the density of concrete is. Tell me what it is. Let's do ourselves a wee favour. Let's assume that BH, BB, and BL for the ballast are all the same. They're all equal the same dimensions, so it'll be a cube. Right? Let's just assume that. Made out of concrete. I want to know the size of that. If you can do that for me, that'll be great. Now, I'm not going to be foolish. I will release, not just to the people who've done the last week's tutorial, I'll give you written feedback, but I will also give out the answers, just the answers and the workings for everybody else as well. Otherwise, it's a bit unfair. But at least if you do it, you get one-to-one feedback from me, written format or verbal. But it'll be written this week. Okay, what we'll do is we'll stop this recording and we'll pop up to E32 where it's significantly warmer than here.